Okay, I'd like to thank the conveners for the invitation, but not so much for the title they assigned me, to predict the future of volcano geodesy in 20 minutes. As you probably know, prediction's difficult, especially about the future, but we can probably safely make a few statements, and that's primarily that the data is going to continue to improve. Matt just talked about satellite data, so I won't say too much about that. I think we're going to see improvement in continuous GNSS. We could talk about seafloor geodesy, gravity, strain, and tilt. I highlighted GNSS because all the examples I'll show you today relied on having continuous GPS time series. But rather than start from the data, I'm going to start from what I think are some key questions that we'd like to answer. We'd like to know what's down there. We'd like to know the volume, shape, size of magma chambers. We'd like to know something about what's in those magma chambers, how many volatiles are there, because that controls explosivity. We'd like to be able to forecast the time, location, and magnitude of future eruptions, and we'd like to say something about the nature of those eruptions once they initiate. And I put a little asterisk here because I'm thinking here about physics-based forecasting, not empirical forecasting, which I think Matt was alluding to and we're going to hear more about. But I'll call your attention to the National Academy Erupts report, which one of the grand challenges was to forecast the size, duration, and hazard of eruptions by integrating observations with quantitative models. And so that's the direction we're working at and I want to focus on. But before I go there, I have a 2-slide tutorial on volcano geodesy for the atmospheric scientists and the cryosphere people in the audience. Basically, what happens is that magma rises from the source region in the upper mantle because it's buoyant. It accumulates in crustal reservoirs. As the pressure within these reservoirs increases, we get swelling of the volcano, so-called inflation. This is measurable by a variety of techniques. At some point, a threshold is reached, and magma exits the chamber, either through a dike or through a long-lived conduit, get decrease in pressure and deflation, so vertical displacement and inward moving displacements. So on the bottom, I show a time series of tilt from Pu'u'o'o eruption on Kilauea volcano, and up is inflation, down is deflation. So you see these inflation, deflation, inflation, deflation cycles. Each of these deflations was associated with a high fountaining phase at the volcano. Now, typically in volcano geodesy, we interpret these data through elastic models. I will call these kinematic models. The longest, the most historical is the so-called MOGI model. That's an approximate solution for a spherical magma chamber, an elastic medium. And so the reason this is widely used is it has such a simple analytical formula. The vertical displacements are plotted here, both vertical and radial. And I want to call your attention to a few things. First of which, the rate at which they decay, the displacements decay away with distance, scales with the depth. So just by noting the spatial extent, you can say something about the centroid depth. The amplitude, in any elastic medium, the displacements are going to be proportional to the pressure change. But it turns out that the amplitude actually scales with the pressure increment times the radius cubed. So it's the product of the pressure and the volume. So we can't uniquely say anything about the volume itself unless we independently constrain the pressure. On the other hand, we can say something about the change in volume because that same product involved. So we can get the change in volume, the depth, and something about the source shape. So there's been a lot of work in the last several decades looking at more general source geometries, getting better Green's functions, including elastic heterogeneity and topography. I want to focus a little bit in a few minutes on viscoelastic effects because we wouldn't expect that you could put 1200 degree C magma against crustal rock and imagine that it would stay perfectly elastic. So we would expect some region around the magma chamber to behave in a viscoelastic fashion. And even in the simplest model, that changes the relationship. So now displacement's not proportional to pressure, but it's actually a convolution of pressure rate history. That's shown here. The convolution is with viscoelastic relaxation functions, which depend, in a Maxwell case, on the characteristic relaxation time, which is the ratio of viscosity to shear modulus. So unless we know the viscosity quite precisely, which is very difficult to do, we can't do this deconvolution and get at pressure. So a couple years ago, I thought that maybe we could make some progress by looking at what happens following an explosive eruption, because eruptions that take hours to days, say, are much faster than viscoelastic relaxation times. They're effectively instantaneous. So we looked at a very simple model, highly idealized, of a spherical magma chamber with a spherical Maxwell shell. At time 0, we have a pressure decrease due to an eruption, and we would expect a couple of things to happen. We would expect relaxation of the viscoelastic medium. We might also increase the flux of magma in from the mantle because the pressure gradient is increased. We have to conserve mass, so the flux in is balanced by the mass change within the reservoir. We take the simplest assumption and make the mass flux proportional to the pressure gradient. Mass can change by changing the volume or by pressurizing the magma because it's compressible. Now, in the elastic case, models like this give rise to exponential repressurization, so you have a pressure drop and then 1 minus exponential recovery, where the characteristic time is given by this expression. And remember, for an elastic medium, the deformation is proportional to the pressure change. So this is showing a tilt record at Krafla volcano in Iceland, and you see this very characteristic sawtooth inflation, deflation, inflation, deflation. Looks a lot like this. I'll come back to that. In the viscoelastic case, of course, things are more complicated. As I said, deformation is no longer proportional to pressure. One of the most interesting, I think, surprising things that fell out of this analysis of this idealized system is that you can get partial reinflation without any new material moving into the magma chamber. This occurs only when the magma itself is sufficiently incompressible. I'm going to measure that by this non-dimensional ratio, which is the chamber compressibility. Chamber compressibility is just defined as the change in volume per unit change in pressure, normalized by the total compressibility, magma plus chamber. So let's take two limiting cases. When the magma is perfectly compressible, what happens is the pressure drops and then it stays constant. We would expect deflation co-eruptive and then continued post-eruptive deflation. In the other limiting case, when the magma is perfectly incompressible, the magma chamber can't creep in. And it turns out what actually happens is the pressure goes up and you can actually get partial recovery in terms of displacement in the elastic medium. So this is a theoretical result. Does this occur in nature? Well, it actually reminded me of what we saw following the 2004-2008 eruption at Mount St. Helens. This is the same volcano that erupted explosively in 1980, extruded a number of dacite spines between 2004 and 2008. You can see the horizontal displacements moving in as the pressure decreased. If we look at the time series at JR01, we see deflation during the eruption, and then following the eruption, apparent partial reinflation. So is this an example of what I just mentioned? Of course, this is not a spherical magma chamber. The eruption wasn't instantaneous. It took 3 years. So I couldn't do an analytical analysis, but we did finite element calculation. I took a chamber geometry consistent with geodetic inversions, and I forced the efflux to match the measured extruded volume to get a pressure history, and showed that there are cases where you can get partial recharge. So what we see on the left is the pressure decreases during the eruption and then recovers. There's no recharge in this calculation. Plot the vertical displacement at the symmetry axis and the radial displacement at the source depth, which is about comparable to JR01, and you can see if the magma is incompressible enough, you can get this partial recovery. This certainly doesn't show that this is what happens, but I think it suggests that we have to look at this possibility more seriously, and we'd like to look at data from other time series. Moving on to forecasting eruptions, in my group, we've put a lot of emphasis on trying to combine seismicity and geodesy, because these are the two most important geophysical indicators for impending eruption. Empirically, these are looked at together, but not in quantitative analyses. We're going to look at this in the context of a very large dike intrusion in Iceland. This is from Freistein's paper. You see the caldera here. This is a 40 or 45 kilometer long dike. It's mapped out in terms of the epicenters of the earthquakes, which are color-coded in time. So the dike propagated here and eventually erupted in this region. These are continuous GPS time series, again color-coded. So what happens is as the dike intruded, it's pushing the walls of the crust apart, and we see the GPS stations moving farther and farther away. How do we do a joint inversion? Well, the hypothesis here is that deformation and seismicity are two manifestations of the same process. And furthermore, that on the time scales of hours to days, that elastic stressing dominates over thermal effects. So we think the earthquakes are just seeing the stress changes induced by the dike as it propagated. So if we can model the opening of the dike, we can compute the stresses. In our calculations, we vary only the length and the pressure and use that to compute the opening through elastic Green's functions. We can compute the displacements. The tricky part is associating the stress changes to seismicity, and maybe we'll save that for the discussion period, but we can put that into a joint objective to model the both data sets simultaneously. I'm showing here just a fit to the continuous GPS time series. This is the work of PhD student Elias Heimsen, where he's modeling just the length and the pressure as a function of time to fit the GPS data, and you can see it does a pretty good job of matching the displacements as they change. Now the next figure, I'm going to show an inversion for the dike opening and length, where he's used the seismicity to control where the dike is, and then used the GPS data to control the opening in the dike. So this is now vertical section, here's depth. What you're seeing is the dilation of the dike in meters here in the opening. Of course, the little dots are the earthquakes, and you see what happens is that the dike evolved in a very irregular, kind of jerky fashion. It stalls for some period of time. The dilation, the opening continues, we know that from the GPS, and then it will jump forward and propagate down rift rather rapidly. Using these kind of models, Elias is able to obtain a reasonably good fit to the data. I'm showing the observed, I should say, this is distance along the dike and time. The black dots are the observed earthquake epicenters, and the red are the simulated. So he can actually obtain a reasonably good fit to the data, but I want to emphasize it requires that the pre-stress and or the frictional properties to be extremely heterogeneous in the crust. And so we have to think about how we're going to utilize that in a forecasting sense, and I think there's a lot of future work in terms of coupled flow and solid deformation modeling as well. Okay, so that addresses the potential of how we use earthquakes and deformation in terms of forecasting how, or imaging how dikes are evolving in space and time. Now we want to address the question of what happens once an eruption is initiated. We're going to go back to Mount St. Helens and the work of Kyle Anderson, now at USGS, and Yingqi Wang, who's here at the meeting. And the idea here is that we can gain more from the GPS data if we couple, instead of having just models where the pressure change is arbitrary, where the pressure has to be consistent with the physical model of the eruption. So we take rather simplified models, although you may think they're fairly complex, but of a magma chamber here coupled to a cylindrical conduit where magma extrudes to the surface. We have to balance, we have to conserve mass and momentum within the system. We have to account for the complex rheology as crystallization occurs and viscosity increases. We have to account for gas loss and so on. I'll talk a little bit more about that. But before, let me just show you from Kyle's work the advantage of this kind of an approach. So Kyle was able to do Monte Carlo MC-MC inversions to estimate the physical parameters that are unknown and find reasonably good fits to the GPS data, as well as fitting the extruded volume as a function of time. So we know the efflux. This is from differential DEM measurements. And what he was able to obtain is considerably more than you would get from the standard volcano geodesy kinematic inversion. As I emphasized before, what you get from that is you get something like, you get the centroid depth, you can get something about the volume change, and it turns out you can get the aspect ratio. We know this is a prolate ellipsoid, but again, you can't separate volume and pressure. You get the product. With a physics-based inversion, because you have many more constraints, this has to be physically consistent, okay? You're able to actually estimate volume and things like dissolved water content. So Yingqi has been improving on these forward models by including equilibrium crystallization. So as pressure decreases, crystals form. This causes the viscosity to increase and leads to a transition from viscous flow to frictional sliding. She also includes vertical and lateral gas escape, because as pressure decreases, gas comes out of solution. This is a sample of the steady-state conduit models. I don't have a lot of time, but as pressure decreases, the volume fraction of solids increase, As you can see here in red, this causes the viscosity on a log scale to increase, and that gives rise to a very rapid switchover between viscous flow and frictional sliding. Similarly, as the pressure decreases, gas comes out of a solution, reaches a percolation threshold where we have interconnected porosity, and then gas can escape. What this means is we now have many more observables that can be put into these calculations. It's not just GPS and extruded volume anymore. We can actually use the fact that we know the porosity of the dome rocks. We can use petrologic information and other seismic information. So just as one example here, let's look at the effect of gas loss, because the permeability is proportional to porosity cubed. So these show the MC results. This is the prior distribution. In red, we have the posterior. And basically what happens is if we know something about the water content within the magma, and we know something about the porosity of the extruded materials, that constrains what the permeability has to be to make that match up. Okay, so I've talked about a lot of things that we do know, now a few things that we don't know. I mentioned before this sort of characteristic sawtooth-like behavior that we've seen in some volcanoes. In other cases, we have episodic inflation, which we really don't understand its cause. This is a summit crossing baseline at Kilauea. Actually, Ahup was one of the GPS stations that showed up in the ionosphere talk yesterday. This crosses the baseline and showed between 2003 and 2007 there was rapid inflation, which actually led to an eruption. We know there was more material coming in from the mantle. We know that from CO2 data, but we don't know why. What led to this episode? Similarly, in silicic calderas, this is from Emily's work at Long Valley, from a combination of leveling, EDM, and GPS. You can see there are episodes of rapid inflation. So what's causing these? Are these individual dikes that are coming in from the mantle, delivering packets of magma? Or do we have long-lived conduit systems where we have nonlinearity because of pressure-dependent geometry? Or are these somehow related to decompaction waves in the mantle? Volcanologists, so that's one set of questions. Volcanologists are moving now to models that look more like this, where they're multi-level chambers with mushy material in between. What do the deformation signatures do to models like that? What should we even be looking for if this is what's really going on? If magma's leaving the mantle and intruding the crust, we should see mass has to be conserved. We typically don't see evidence for the source region. Now, we tend to argue it away, saying it's too deep, the amplitude's too small, but this feels a little bit like pushing a problem under the rug, and I think we need to address that. And then finally, can we get at total chamber volume? From a hazards perspective, probably one of the most important things to know is just how much is down there that's eruptible. And I've pointed out one perspective how we might approach that, but I think there are other avenues for the future that are promising, I'll say. Okay, so I'll stop there. Thank you.
So I really like this idea of the physics-based approach. One of the difficulties is that a lot of the really interesting things that you're bringing up require us to have knowledge of the products that are coming out. And so that really requires us to look at stuff that has happened in the past, but particularly like for silicic systems like Long Valley, you know, the things that have come out in the past have been wildly variable. And like the deformation that we're seeing right now occurs in an area that hasn't really erupted in a very long time. And the products that we're seeing, you know, the more recent eruptions have occurred much more along the periphery. So do you want to comment on that?
Yeah, no, that's a good point. So in the modeling of an ongoing eruption, so in the case of an effusive eruption that lasts for a long period of time, you can make use of the materials that are actually erupted. For explosive eruptions, obviously, that's much more challenging. A slide I had to take out in the interest of time is actually from Freistein and Sigrun Hrensdottir, where they looked at an explosive eruption. This isn't looking at the products, but looking at the flux. And they estimated the flux from the, I wonder if I have that. Yeah. I think this is a remarkable result. So these are scaled GPS displacements in black, and the volume flux, which was estimated from the column height of the erupting column. And these two track one another remarkably well. And what this indicates is that this is really important information because it tells you that the geometry of the system's not changing as a function of time. It tells you the compressibility of the magma is not changing. So here's a case where you don't have time to pick up the pyroclasts and look at them, but just using information from the eruptions as it's ongoing tells you a huge amount. And I think we really need to monitor these, have more systems that are monitored in examples like this. But you're right. For these holistic systems like Long Valley, we can't use the erupted products because they're so variable to tell us what's happening right now.
I'm just wondering also, volatiles that might be leaking out beforehand. Do you think that there might be some useful information?
Absolutely. So I did have a note on that in the kinds of calculations we're doing because we're conserving mass of not only the melt, but also the individual volatile phases. If we had CO2, continuous CO2 emission data at St. Helens, we could have incorporated that in the calculation, and it would have been an important constraint. So clearly, harking to Matt's talk, we're not going to have this level of monitoring at all the world's volcanoes. But I think we need to get it beyond just a handful if we're really going to get at the underlying physics of what's happening.
Another question?
I was just wondering if you could make a longer comment on what you see as the potential role of seafloor geodesy in the future of volcano geodesy and physical models.
Let's see if I have a slide. Yeah, so the oceanic environment is actually not an optimal place for doing geodesy, but it turns out to be a very good place for doing seismic imaging because you can take industry-level marine seismics, and this has been done at Axial Volcano in the Montefuca Ridge. And Chadwick they have seafloor geodesy. It shows these inflation deflation cycles. In this case, it looks these eruptions are actually inflation predictable, but there's extremely high resolution seismic imaging that would be very difficult and expensive to do on land, but you can do in the marine environment. So we ought not, there are obviously many volcanoes along the mid-ocean ridge system that are underwater, and even though geodesy is difficult in these environments, I think we ought not to forego them because of the potential of using seismic imaging. This is an area where this can give us important constraints on the total volume of what's down there.
Last question? Paul, you showed us an image from the paper by Kathy Kasman with a very multi-level magma chamber with mush in it. Is there a discord between our volcano geodesy models and these kind of views of many volcanologists that the magmatic systems are very heterogeneous, and do we have a way to address these heterogeneities?
I think it's an important challenge. I mean, I don't think we even know what we should be looking for because we haven't run forward models with these kinds of systems. So I would claim we don't even know what we should be looking for, if that's what's really going on. Now, that may not be what's going on, but that's one image of what people who are studying petrology and geophysics think are happening.